And I'm Haley Blake.
Our advisor is Dr. Stern.
So what is Wavetap? Wavetap is a subset of NSC technology. It's a subset of radio frequency identification called NSC technology that operates on a wavelength of 13.56 megahertz. It communicates. We're going to use a tap card, which is going to have an NSC chip inside, and it's going to communicate with the module, which you'll see on the next slide. And it will communicate, the internals of that is going to go into the electromagnetic block that's going to be installed on top of the door. And depending on whether or not the user is in the database, it will allow you access. So on the next slide, this is our module. As you can see, we have the isometric view, the bottom view, the front view, and the left view. On the left view, there is a cutout that is to connect to an external power source.
So some constraints for this project is that it has to be done within 2 semesters like everyone else. So completed before April 2025, and then we only have a budget of $500 since this is not industry sponsored. So we're going to get into our requirements and specifications. So first things first is our mechanical requirements. I'm going to briefly go over what we wanted to hit here. So we wanted to make sure that everything is able to withstand the weather patterns that we see in Northeast Pennsylvania. We're planning to have our lock system outside. So we wanted to make sure that it's not going to be affected by the rain, wind, snow, or sun. We also wanted to make sure that it's able to withstand the weight of the electrical components and be within a certain amount of distance from the door that we decided was about 2 feet. And then we wanted to be safe from vandalism as well to make sure no one can break in and steal any of our components. So in order to hit these requirements, here are our specifications. We're going to be 3D printing the housing in ASA material with a UV stabilizer. We're also making it a 5 by 5 by 5.5 inch box. We are also making it 0.1 inch thick to help counter that weight, and use security screws as well as regular screws to make sure no one can break in and everything is connected to the mounting plate. And we got a board provided to us by facility, so thankfully we are able to test our system with the provided board.
For electrical requirements, we need to make sure the input voltage is 120 volts AC. This is because we're trying to make a replacement for the current swipe access system. So it's going to be plugged right into the wall, so that's why we're using that. Then we're going to have a single voltage source, so this system can connect directly to any circuits that's in the building itself. We're also going to use a 13.56 megahertz frequency. This is the standard frequency for NFC technology, so we're going to use that to connect to the Raspberry Pi itself. Then we're going to make sure there's an access size display and a automatic door locking mechanism for the user. And then all electrical components need to be properly grounded and fit inside the housing. So for our specifications, we're going to use 18 American wire gauge wire. This will supply the 120 volts AC into the housing itself. Then we're going to use a 24 volt center tap transformer. This will supply 2 12 volt AC loads to the circuit. Then we're going to use an NFC reader. This will use that 13.56 megahertz and connect to the Raspberry Pi. Then we're going to use LEDs. These will show if the system is green, which means if the door is unlocked, red will be the door is locked, and yellow will be standby mode. Then we're going to use a 5x5 timer. This will start a 10-second timer. So when the tap card is touched to the housing itself, it'll send a signal to the Raspberry Pi, which will send it to the 5x5 timer and start at 10 seconds for the door to be unlocked. And then once that's completed, it'll lock. Then there will be AC and DC ground on the PCB board or printed circuit board, and all the components will fit on the 2x4 inch PCB.
Alright, so for software requirements, it's split up into 3 major parts. We have the embedded part, which is the Raspberry Pi module. And then for the front end, it's going to be a website with the back end being a database. Now for the specifications, the database is going to be done through MySQL. And as I said earlier, the embedded module will be the Raspberry Pi 4 Model B that, there's the transformer on the left, along with the PCB board and the buck converter. And then underneath that, to hold all of it, is the mounting plate. And the mounting plate and the main component of the housing are going to be 3D printed as mentioned earlier. And to connect them, we have threaded inserts that we're using to not compromise the plastic of the housing. So we're going to use the threaded inserts instead and put the tamper-proof screws in.
So in order to prove that our housing is able to withstand the loading that we're going to be putting on it, we did some calculations and ran a simulation. So first we're going to go over the calculations. So we did this, we got a safety factor of about 2. This is using it as a cantilever beam and with a point mass system. So we'll see a different type of system in the simulation.
So this is the simulation ran through SolidWorks. This is the safety factor we got using a distributed force on the inside face of the bottom surface. So with that, we got a minimum safety factor of 1.2 using a distributed load. On the next slide, it'll show you the shear stress that we've obtained. We got a maximum shear stress of around 1,300 psi. And then on the next slide, we have the displacement. So the maximum displacement or the maximum deflection that the object will face under this loading is about 0.12 inches.
So here's the electrical design of the circuit. So this will show the flow chart of how we're going to connect everything together. So on the left shows the 24-volt center tap transformer. This will supply those 2 loads. So the top will be a full wave bridge rectifier, smoothing capacitor, zero diode, converting that 12 volts AC to 12 volts DC. And then we'll use a buck converter to convert that 12 volts DC to 5 volts AC, 12 volts DC to 5 volts DC, right into the Raspberry Pi because it requires that 5 volts DC and 3 amps. Then on the bottom we'll use the same setup up until the 555 timer. That'll have the 12 volts DC. Then I'll send that 12 volts DC to the timer. And in addition, the Raspberry Pi will send a signal to the timer and start that 10-second timer. And the output will use a transistor. That's just to boost the output current and to add a safety feature for the 555 timer and supply the magnetic block. And this is just a zoomed in schematic of our circuit. So this shows the transformer supplying the 2 loads of the Raspberry Pi and the magnetic block. It'll just show the full wave bridge rectifier, smoothing capacitors, and the Zener diodes. These are some calculations. So on the left side, we'll show how we calculated the 12 volts DC that needs to be supplied to the loads. In addition, the power consumption of the load and the smoothing capacitor calculations. The right side will show the tap tube, same calculations, and then the power used is on the bottom. This is our 555 timer diagram. So it'll be supplied by 12 volts DC, and then the Raspberry Pi will supply the trigger signal from GPIO pin 23, and it'll output through the transistor to the magnetic block.
Now going into the software design and components, I wanted to highlight the key components that the software is needed to run. I chose a Raspberry Pi Model 4B because it contains 4 gigabytes of RAM and has the ability to have onboard storage. It can store quite a large quantity of data because I want to be able to download the database in case if it loses internet connection. Because, well, as you know, it has pretty spotty Wi-Fi at times, so I figured it would be better off to move it through that way. Now, going into the NFC reader itself, it comes with a pre-tuned antenna, which is at 13.56 megahertz, which is outlined in the International Standards Organization 14,443. And going into the database parameters, I had 2 sets of parameters that I wanted to do. I wanted to define it by the users, which when they log into the website, will separate them between administrators and users. And then I wanted to sort it by building rooms and IDs because there are different rooms, and I want to be able to identify the different boxes in case if they're vulnerable to define them. Then I wanted to go into the actual permissions of them. Here's a basic diagram of how the software is going to be implemented. We're starting off with the Raspberry
now we're going to get into all of the management components of the project. So first, I broke down the work breakdown structure into two parts so it's easier to read. So this first part of it is mechanical and electrical parts. This is just breaking down everything that we went over in the requirements and specifications document. And here's part two of it where it has software testing and management. The testing part of it is showing that we're going to test the software, test the housing, and test the magnetic box separately, and then we're going to test them all together to make sure that they work. And then management, all of our management components that have to be in this. Here's our schedule for the fall. This is highlighting everything that was due, when it was due, and when we anticipated the start date of it. So here is the calendar view of it. Here's our spring schedule. This is just estimated what we're expecting to be done. We're not sure the due dates or anything or what it's going to be due. We just really want to highlight that we're going to have to be prototyping and redesigning the system quite a few times before our spring presentation. Here is again the calendar view of it.
All right, so I just wanted to give a general overview of our budget. For the monetary side, it's going to cost around $360. And then for the costs that would have been the real bill without the donations from the donor and everything, it would have been around above budget. And then for labor, I just calculated that based upon 4 hours a week for 32 weeks, which is about the time between the two semesters. That came out to around $13,800. And Sarah and Dustin will go into more about how we save money.
Yes, so for the mechanical end, thanks to facilities donation of the door and the frame, we were able to save approximately $80 on our end.
And for the electrical side, we're going to be using many components that are already in the lab, so we'll save $60 on that end.
And this is the real life budget of how much it would cost.
And this is the labor cost breakdown.
And for ethical considerations, since we are working with electromagnetic waves, we have to take into consideration all the protocols put in place by the Institute of Electrical and Electronics Engineers, as well as take into consideration the security and privacy of our users, which will go into detail in the next slide.
Here are more of the security considerations. So the NFC cards that we're using comes with 7 bytes of combinations that are possible, which is 2 to the 56 amount of combinations you can use. And also all of the information is going to be behind like a password protected login. And it will depend between users and administrators.
Our test plan for this is, as we stated, we have a door provided by facilities, and we're going to be using a card to be able to see and test if we're able to get into the room, if the access is denied or access is accepted.
And then to conclude, Wavetap will be a tap access system that will allow users access whether they are in the database or deny them access if they are not. And some future considerations we are considering is adding an L-shaped bracket to our design to alleviate some of the loading that it'll experience to get our safety factor a bit higher. We are also considering to potentially connect this to Apple and Google Wallet, but with our time constraints currently, it's not looking like it's going to happen.
We just want to give a thank you to our advisor, Dr. Serini, Dr. Bednar, Swiss University's facilities, IT, and public safety, who helped us design our database, and also GrabCAD and Granger for our CAD files. Thank you.
About your power supply,
Yes.
that's a humongous transformer. You're trying to get 3 amperes at 24 volt center tap. And I don't think you need nearly that much. Can you tell me how big a pulse width you've got to give to the solenoid?
We are not sure of that. It supplies 4 amps output, so it should be well within our parameters for that. The Raspberry Pi draws 3 amps initially, and then after that it only draws as much as it needs. The magnetic lock will draw half an amp for that.
So the point is that it's only occasionally that you need that big pulse.
Yes.
So you can probably get out of a much smaller transformer. I bet that transformer accounts for most of the weight of the system. And it probably accounts for about 25% or 20% of your total electrical cost. You can substitute a bigger capacitor. You can go to a smaller transformer and be able to supply the average current that you're going to need with just storing the energy on the capacitor ready to dump into the solenoid when somebody, the next person comes along. That won't be more than once every several seconds. So look at the average load and see if you can sort of store that energy you need for each pulse on a big capacitor, which is cheaper than a big transformer. Other thing, it looks like you have two independent 12-volt power supplies, and I don't see why you need those to be independent. Why not just use a 12-volt center tap transformer to give you 6 and 12, and use half-wave rectification, just use a bigger capacitor. You've got to regulate what goes to the Raspberry Pi anyway. And you don't need to regulate what goes to the solenoid.
The reasoning for that is because the magnetic lock itself needs 12 volts, and the Pi needs 5, but we'll use a buck converter to make it from 12 volts to 5 volts. So that's why it was separate.
Right, but you could use a cheaper approach to that by just getting 6 volts to regulate down to 5 volts, and use a cheap linear converter. It's not a large current, so it's kind of not worth a big investment. What you're going to get out off of that full wave rectifier is closer to 17 volts if you're putting a capacitor on it, and that's going to give you a big enough pulse. You don't need to regulate that for the solenoid. You're just going to give it that big zap of power every time somebody comes along. So my guess is if you really look at what's going on with your actual loads with that power supply, I think you can get by with a smaller transformer.
Okay.
And a simpler power supply. Thank you.
So I want to put in a bit more extreme. For this application, I feel you absolutely don't need a transformer. It's completely unnecessary. All you need is a commercial DC power supply, like even we use this in electronics lab. There's absolutely no need for you to design that transformer. Plus, if you put a big magnetic field in your electronics together, that causes interference. You don't want it to mess up your electronics. This is basically an electronics project. You absolutely don't want to deal with the power side. Just let the commercial system deal with the power side. Plus, you don't even need a lot of current. You don't even need a power system. It's not even a power system. You see what I mean? You're just dealing with the electronics. Just a commercial DC power supply plugged into the wall, give it a nice little 12 volts. That's all you need. Why would you need a transformer? Absolutely unnecessary, completely unnecessary. So that's my first comment. Because just that thing was so close to all the other electronics, you're going to have unexpected consequences. You see what I mean? Because if you put the whole thing in a big magnetic field, so it's completely unnecessary. That's my first. The second, could you go back to slide 21? I know, like from a kind of application perspective, you want to apply the electronics, like the electric stuff you need. You see what I mean? That might be the reason why you went with the transformer project. For the sake of this project, you absolutely don't have to do that. It's completely unnecessary. Because second, you see here, like I just look at their very easy mistake. I mean, 12 times 3, that's not 15. You see what I mean? That's easy mistake. And that just makes me much more concerned about other parts of the system. So with those kind of things, you need to be more careful. Third is that, so what's compare this your system to the current system, what's the main advantage? Things that as an engineer, you always keep in mind that things exist for a reason. It's not just because we are, we are adapting quickly enough. There must be great advantage of the current system. So what's the most benefit you're bringing to the current system?
Case of access. Because currently I know a lot of people are struggling with getting into the building, especially I've had people come up to me and be like, yeah, I've been having to go to public safety a lot to get my car fixed. So with this, you're going to be able to update on the website and request access on it. And also, some people have to swipe multiple times to get in. With this, you would have to just be within 4 inches of it with the card, and then you'll be able to go through it.
I would also like to say
But the reason I'm asking this is I want to treat you guys as a contract entrepreneur. You're trying to create this because you are supposed to sell this at it. I feel that's not a very convincing idea for you guys. I'm saying that's not a convincing argument. Don't get me wrong. There's nothing wrong with keeping this project. But again, if I put them on the customer side, you are closer to sell a whole bunch of this. There must be like a very convincing argument that says why I'm better than your current system. And I don't see that at this point. And that's all.